Let's begin the Vivado design. Start by creating a new project for your desired board, and then add a block design. Download the provided VHDL code for frequency control word from our GitHub and add it to the project's resources. The BRAM is used as a lookup table to save the Sine coefficients. Within the block design, use the Add IP feature to insert a block memory generator. To configure the block memory, double-click on the block memory generator block. In the Basic tab, you'll find two controller operation modes for the block memory. Since in this training block memory is controlled directly by the programmable logic, we need to select native interface or standalone mode. For the memory type, this tutorial uses block memory as a lookup table to store pre-calculated sine wave values. These values are then read from the block memory to generate the sine wave. To achieve this, we will use single-port read-only memory. Go to the Port A options and choose 11 bits for port width. The reason is that we are generating sine wave coefficients with 10-bit resolution for amplitude and an additional sine bit. The depth of the memory defines how many different data values can be stored. Since we are generating 1024 sine wave coefficients, you need a depth of 1024 to store all these values. Additionally, we want the port to remain continuously active, so we set the Enable Port type to Always Enabled. Open Other Options tab to load a memory initialization coefficient file. This coefficient file is used to preload block memory in an FPGA design with specific initial data. When the design is synthesized and implemented, the block memory will contain the values provided in the file. Now press the Browse button and load the COE file. You can validate and then save it. In our design, we use the Accumulator IP block as a phase accumulator. The phase accumulator is the core of the Numerically Controlled Oscillator. It accumulates the phase information by adding the frequency control word to its current value on each clock cycle. Double-click on Accumulator IP block and change the input and output width to 10, then it matches to the address bit width of block memory. When we compare the previous sine generators with this new design, we can recognize that in our previous designs we used a simple counter, and here we are using an accumulator to drive the block memory address. Since we don't want to bypass the accumulator's input to its output, add a constant to the block design, set its value to 0, and connect it to the accumulator's bypass port. Add a simulation clock generator to your design. The simulation clock generator utility is used for creating a simple clock generator in a test bench. Connect all the clocks pinned to this clock source. Now we're going to add the frequency word control. The control word determines the increment size for each clock cycle, thus setting the rate at which the phase advances and ultimately controlling the output frequency. Right-click on the block design and select Add Module. From provided list, you should be able to select the frequency control word module. It will add the module to the block design and allows us to work with our VHDL design like a normal IP block. This VHDL code generates a sequence of values that simulate a frequency control word by adjusting the phase accumulator step size every 20 microseconds. For the first 5 iterations, the step size increases, resulting in an increasing output frequency. In the next stages, the step size decreases, causing the output frequency to decrease. This behavior demonstrates how the code modulates the frequency, creating a variable frequency output over time. Let's make some external ports. It will make our simulation analysis much easier. Create top HDL wrapper and let the Vivado to manage and auto-handle it. Simulation. Now we can proceed with the simulation. Follow these steps. Run behavioral simulation. Extend the simulation duration to 200 microseconds. Reset the simulation and then rerun it for the specified time. Adjust signal settings. Right-click on the simulated signals to change their settings. Set the radix to sine decimal and the waveform style to analog. After these adjustments, you will observe a sine wave is fluctuating at different frequencies. The simulation output signals can be explained as follows. first signal is the output of frequency control word. This signal represents the step size used by the phase accumulator. It indicates the size of the increments added to the phase value on each clock cycle. The output value of FCW changes every 20 microseconds. For the first 5 iterations, the step size increases, resulting in an increasing output frequency. In the next stages, the step size decreases, causing the output frequency to decrease. This behavior demonstrates how creating a variable frequency output over time. Second signal is the output of phase accumulator. This signal shows the accumulated phase values. It forms a sawtooth pattern that increases progressively, with the slope determined by the FCW. A higher step size from the FCW results in a steeper ramp, faster phase accumulation, while a lower step size results in a gentler ramp, slower phase accumulation. The pattern demonstrates how the phase evolves over time, wrapping around when it reaches its maximum. Third signal is the output of the block memory. This is the actual sine wave output, generated by using the phase accumulator's output as an address to read sine coefficients from the block memory. The frequency of this sine wave changes according to the phase accumulator's ramp rate. When the FCW is larger, steeper phase accumulator ramp, the sine wave frequency is higher. Conversely, when the FCW is smaller, gentler ramp, the sine wave frequency is lower. The waveform shows sections of high-frequency output followed by sections of lower frequency, matching the FCW's variations. Now, let's have a look at the block diagram of the design that we just finished it. This block diagram represents a numerically controlled oscillator, NCO, commonly used to generate a digital sine wave with variable frequency. The main components include a phase accumulator, a sine phase-to-amplitude converter, sine pack, and a frequency control word. Here's a detailed explanation of each block. The frequency control word is an input value determines the frequency of the output sine wave. The control word represents the desired phase increment per clock cycle. By adjusting this value, you can change the step size in the phase accumulator and thus control the frequency of the generated sine wave. The phase accumulator is the core of the NCO. It accumulates the phase information by adding the frequency control word to its current value on each clock cycle. The accumulator consists of 2 main components. Adder adds the current phase accumulator value to the frequency control word to produce a new phase. Register holds the current phase value and feeds it back for the next clock cycle. The output of the phase accumulator is a value that represents the current phase of the sine wave. This phase value continuously increases and wraps around due to the finite bit width of the accumulator, creating a sawtooth pattern. Sine phase-to-amplitude converter, sine pack, is essentially a lookup table that converts the current phase value from the phase accumulator to a corresponding sine amplitude. This lookup table stores one period of the sine wave in digital form. This figure represents the output of a phase accumulator with different frequency control words. The x-axis indicates clock cycles, and the y-axis shows the phase accumulator's output. The step size dictates how quickly the phase value grows over time. A larger FCW results in a larger step size, meaning the phase progresses faster. This increase in step size directly affects the frequency of the generated waveform. Thank you for completing this training. If you enjoyed it, please like, subscribe, and share your ideas in the comments below.